Hello students, in this video we'll discuss hyperbolic constant coefficient second order PDEs. Let's recall from our definition of classifying PDEs, recall that a PDE AUXX plus 2BUXY plus CUYY equals 0. So it's homogeneous constant coefficient second order. So homogeneous constant coefficient and clearly second order, right? Great. Now we said it was hyperbolic, was said to be hyperbolic. If the eigenvalues of the corresponding quadratic form, if the eigenvalues, if A, B, B, C has opposite signed eigenvalues, And there's cool methods we can do to solve these things over here. So for example, we've seen in previous videos that the wave equation has this nice factorization, but you can do the same thing for general linear, the same thing for a general hyperbolic equation as well. That's constant coefficient. So let's recall that to solve, solving the transport equation, if I look at, say if I look at fx plus b fy is equal to 0, that's a simple transport equation just with x's and y's. And so how can I solve this? The solution to this, f of xy, is just an arbitrary function phi. And then I need, if I do a y derivative, it has to have a b. So I'm going to have an x. I'm going to have bx minus y. bx minus y. Let's check to see if that works. Well, if I do a y derivative, I think I'm going to get a -1, x derivative of b, it works out fine, right? So in other words, the solution of this problem over here, it looks like this. If we were to put an a over here, a fx plus b fy equals 0, then the general solution f of xy is going to look like what? Some arbitrary function. When I do an x derivative, I have to get a b, right? So it's going to be a bx minus a y. Beautiful. Okay, let's check to see if this works, right? So if I do an x derivative of this thing, I'm going to have an a times b. If I do a b derivative, if I do a y derivative, I get a negative a, so I have a negative ab times the derivative of psi. So I get 0. Perfect. So this is the key feature that we're going to use over here. With a secondary feature, I'm going to treat this as a differential operator. So in other words, what we'll say is we'll say that I'm going to recast this expression and say the following. We're going to say that if I have an a d by dx plus b d by dy applied to what? Applied to a function, psi, which looks like bx minus ay is equal to 0. So in other words, these functions over here are in the kernel of this differential operator. Now the beautiful thing is that differential operators of constant coefficient, we know from ODE that they commute. Same thing happens in PDE, right? So now note, here's a remark or a proposition. A d by dx plus b d by dy, and then c d by dx plus d by dy is equal to c d by dx plus d by dy times a d by dx plus b d by dy. Okay? In other words, these constant coefficient first order differential operators commute with each other. Let's check to see if it works. If I did this, I'd have an ACXX. If I do the same process, I'll have the same thing. I'll have ACXX, right? Because it comes from the fact that the differential operators are linear and the coefficients are constant. So there's no cross terms that pop up by the chain rule, right? Which is beautiful because now what can we do is we can use this kernel argument to find general solutions to hyperbolic problems, right? So let's see an example of this. Here's an example. Let's solve the PDE. Let's solve the PDE. It's going to be UXX minus uxy, and then plus 6, or let's do minus 6 uyy is equal to 0, okay? So you might say, well, wait a minute, this is a sort of a crazy thing over here, but let's try to factor, right? So factor. Okay, so what's this going to look like? So in other words, what I have over here is I really have d squared xx, the operator d squared xx minus d squared xy, and then minus 6 d squared yy applied to u is equal to 0, right? Well, what can we do? We could factor this as how? We could say that this is really d by dx, then minus 3 d by dy, and then d by dx plus 2 d by dy applied to u is equal to 0. And I can easily take this first factor over here and make that equal to 0 because it's of this form over here. So what's the solution to this first thing over here? So my u of x and y is going to be an arbitrary function phi, which we don't know, right? It's an arbitrary function. And now my b is equal to 2, so that's going to be a 2x, and then a minus y. Because I plug in anything of this form over here, what's going to happen? If I do a x derivative, I get a 2. If I do a y derivative, I get a negative 1 times 2. It works, right? Then equally well, what could we do? Equally well, we could flip the order of these differential operators, right? And then I could say, oh, how can I annihilate this thing over here? So then I'd say plus another arbitrary function psi. And then what will happen over here? Now my b is equal to what? My b is equal to negative 2 or negative 3. So I can just replace it with this. Since I have two negatives, I can replace it with a positive, right? So this is going to be a what? This is going to be a 3x plus y. Let's check to see if that works. Indeed, it does work, right? So in other words, u of xy is this expression over here. So my solution involves two arbitrary functions and so therefore it's a general solution. Hence, this is a general solution. So the remarkable thing is that with these constant coefficient equations, you can factor them, right? Now I had to pick a hyperbolic problem over here. And the reason I had to pick a hyperbolic problem is because I needed the roots of these, this thing as in some sense, a polynomial in x squared and y squared to have real roots. If there are complex roots, you can still do this, but now you have functions of a complex variable and take real and imaginary parts. And that's what we expect because with the Laplace equation, we know we have these e to the x cosine y type solutions. So it's feasible that we can use the same methodology for those complex valued solutions. But for these linear constant coefficient hyperbolic problems, you can solve these problems like this. If this was a third order equation that was hyperbolic, I can do the same trick as long as I can keep factoring, right? So it just becomes a question of how quickly and efficiently you can factor these things. But you can use this general idea that since these differential operators of constant coefficients commute, right? So there's a commutation of these things. It's easy to check this proposition. What you can then do is you can factor because then you can concatenate, these operators concatenate to what? AC d by dx squared, right? And then BD d squared by 2y derivatives. So there's a very, very powerful mechanism that's exactly akin to how we solved ODEs. So yet another example of how the methodology from ODEs persists into the method of PDEs, which is very, very helpful, and we'll see this as a constant theme throughout the course. Thank you very much.